chapter 16, transverse waves, transverse traveling waves, this equation. Then we said if we take the partial derivative of that, it gives us the velocity in the y direction. We got negative a omega cosine of kx minus omega t plus phi. Then we take the second derivative of that. We get negative a omega squared sine of kx minus omega t plus phi. Then the other things we developed are the meanings of the k. K is 2 pi over its wavelength. Omega is 2 pi times the frequency. Velocity of the wave is the wavelength times the frequency. Or we can write it as velocity of the wave is omega over k. Then we developed equations for the average energy of a wave, the wave. 1/2, what was the equation?
Why is it negative?
Is the derivative of this with respect to t. And then negative omega comes out. Yeah. And then the average energy of the wave. See that one? So the energy of the wave was 1/2, and we derived this equation. So 1/2, the mass density of the wave times omega squared times amplitude squared times the wavelength of the wave. So that's the average energy that it carries over one wave. So the power transported, then you divide that by the time, which is the period of one wave, and you get lambda over the period is v. I think that's kind of where we ended pretty much. The next thing to mention is also the relationship between the velocity of a wave and the medium that it's going in. So in this case, in chapter 16, we're discussing waves in strings. We're focusing on that. So then we want to know what's the velocity of the wave with regard to the tension in the string and the mass density of the string. So we can Google that. Velocity of wave in a string. Okay, so with you get this famous equation that the velocity of the wave is equal to the tension in the string divided by the mass density of the string. So if the string has some tension in there, in newtons, right? So if you want to, basically, if you want the wave to travel across a string, the string can't be loose. Then you're not going to have any wave in that. So you first you tighten it, give it some tension, and then you disturb a portion of it, and then the wave can travel. So then the velocity d depends on how much tension you put. So velocity is equal to square root of tension divided by the mass density of the string. This is tension. So don't get that confused with this t here, the period of the wave. Right? The period of the wave is, this one I'll probably write it like a t with a little two hanging lines. That's one over the frequency of the wave. So tension is very different from that. And then divide that by the mass density of the string, which is the mass of the string divided by the length of the string. And that's mu, is the mass density. Mass density. It's mass per unit length. So the units, if we do a unit analysis again, the units should give you units of meter per second squared, right? So you got your newtons over kilogram per meter, right? And then, so the newtons, well, remember newtons is a kilogram meter per second squared. If you divide that by kilogram per meter, kilogram cancel, you get square root of meter squared plus over second squared, right, which gives you meter per second. So if you always do unit analysis, it should always give you the units of what you need, right, meter per second. The other thing we can ask is to, more on a foundation basic level, why should the velocity depend on the tension? Why is it that if I increase the tension, the wave travels faster, but in a thinner string, the wave travels more? So in order to have a wave in a string travel fast, you need the wave to have a high tension, the string to have a high tension, and then you need the string to be light, you see. So of course, when you apply that to musical strings, the thicker string is going to have a smaller velocity, right? The thinner string is going to have the faster velocity. Well, this is the formal derivation of that.
To derive a formula for the speed of wave on the string. Here's the pulse that we're going to be considering. It is traveling from the left to the right along the screen here. Now imagine yourself in the reference frame of the pulse. So you're traveling along at the top of the pulse here. You're this increment delta S. What you see is increments of the rope going past you. They'll be traveling to the left. Okay, now let's consider what's happening in this case. Delta S is a little arc length here. R is the radius of our semicircular hump. Theta is the angle between the middle of our arc length and the edge of our arc length. So the total angle in here is 2 theta. So from our equations for arc length, we know that the length delta S is equal to 2 r theta, because the angle is 2 theta and the radius of our semicircle is r. Now we're going to have a think about all the forces acting on the system. We have tension pulling the string down in this direction. We have tension pulling the string down in that direction. Those are the 2 forces acting on it, and the result is that this undergoes circular motion. And so the resultant force is equal to mass times the centripetal acceleration. This makes the geometry a bit more clear. The tension is pulling on the end of this increment down here and on the end of this increment here. Because the radius makes an angle of 90 degrees with the circumference of the circle, this is 90 in here, so this angle in here is equal to theta. Okay, so that's just the same picture again. Now what we do is we move this tension here this tension here so that we're adding them head to tail. When we do that, we know that our resultant force is the mass times the centripetal acceleration. So looking at the geometry, this angle in here was theta, which tells us this angle here is theta. So half the length down here is t sine theta. So the length of this resultant force is 2t sine theta. So that's why we've got this 2t sine theta here. And here is our centripetal acceleration. Now we're going to make the small angle approximation. If theta is small, then sine theta is approximately theta. So we can replace this sine theta here with theta. That's what we've done here. Now what we need to do is work out this mass here. So the mass of a piece of string is equal to the density per unit length of the string times the length of the string. But we've already shown that the length delta S is equal to 2r theta, because it was the arc of that circle. So we can say that the mass of the piece of string is the linear density times 2r theta. So now we're just going to substitute that in. Here's our resultant force, 2t theta, and here's the m v squared on r term, and m's been replaced with this expression here. Now there's lots of things we can cancel out. We can cancel out our thetas, we can cancel out the 2's, we can cancel out the r's, and when we do that, we're left with the expression t is equal to mu, the mass per unit length, times the velocity squared. So we can rearrange that to write that the velocity is equal to the square root of the tension over the mass per unit length.
Awesome.
Now, we assumed that this was a semicircular pulse. It actually...
So let's write that down, that's the formal derivation of that equation. So unit-wise, we already see that it works. So they're saying, imagine the wave traveling this way, right? And then focus on what's happening to a certain element of the wave. Remember, the certain element of the wave is just going up and down. So when it's at the upper portion of its path, what are the forces on it? So they're getting an increment delta S. They're saying there's tension T pulling on it, right? Like that, on that element. So it's like this kind of, and then like that, right? And then this is going to be theta, this is theta, and then that has a centripetal acceleration AC this way, right? So then they're saying 2t sine of theta is equal to the mass of that, which is dm, times v squared over r. And v is the velocity. V is the velocity that the wave is traveling this way, you know, as it's passing by. You see, so it's not this velocity v sub y. That's not that. It's the tangential velocity of the wave going this way. That it's the velocity of the energy of the wave, not the velocity of the element of the wave. See, that's a distinction. So this isn't this guy at all. That's the velocity of the energy of the wave. You see. So then this is the radius of that circle that it's making. Right? So it's an imaginary circle. So then it's going to say, the next thing that they did is to say dm is the mass density times the length dx. Right? And then the length dx is going to be this whole length from here to here. And then that's going to be what? Whatever your circle is, right? This is r. So then they're going to argue this theta and this theta are the same, and then this theta is the same. So then dx is the total length of that string, right? Is going to equal r times 2 theta.
Why is there centripetal acceleration?
Whenever a roller coaster, this is a physics 1 problem. The roller coaster is going like this, right? At the top of its path, it has circular motion. This is a physics 1 problem that we do in chapter 6. We got the normal force, we got the mg, and we say the centripetal acceleration is down, and we say mg minus n is equal to mv squared over r, if you remember chapter 6. the roller coaster problems, right? So that's what the string, that's what the wave is. The wave is going like this, you know, like that. You see? So the velocity that the wave is traveling at is like that. That's the velocity of the wave, right? It's not, the difference between the roller coaster is you're traveling literally like that. In the case of a traveling wave, the energy of the wave is traveling like that, but the string is just going up and down. You see? So it's a bit different than the roller coaster problem, but the same physics holds true on that certain element of the wave. At a certain point, that element of the wave, there's an energy coming through it. You see? It's as if the string is acting like the train track over which the roller coaster is riding. That string is acting like the train track, and then the energy is traveling at a velocity v. You see? And then you're going to say dx is equal to r2 theta, and then that's where a lot of the cancellations will happen. Oh, then they're going to make this. They're going to make the small angle approximation. Now, how do we know the small angle approximation holds here? Right? In other words, in which case can we argue small angle approximation? Because sine of theta, it certainly wouldn't be true if we're taking a huge portion of the string, right? Imagine if we're taking a huge portion, then this is the tension T, this is the tension T, this is theta, and then this is the circle, right? Okay. And this is theta. It still would be true that this would be theta and this would be theta. That would still always hold, even if the length of the string was long. However, when you get to this point, you can no longer say sine of this angle is equal to the angle. You cannot say that, okay? But why in this case we're going to take a small element of the wave? Well, because we want to know just the tension on that little portion of the mass and its relationship to the velocity of the wave traveling to that little portion. So we're taking the limit as delta x goes to 0, essentially. So then when you decrease this and squeeze it in, then you can say, yes, sine of theta is the same as theta. So then it cancels out. Then theta cancels, 2 cancels, r cancels, v squared is equal to t over mu. Beautiful derivation of that. This is a famous equation, so it's a really beautiful derivation of that. Okay, so that's going to be one of the equations that will use the dependence of the velocity on the tension of the string. After we're done with this chapter, then we're going to go to sound waves. Then we're going to talk about what's the dependence of the velocity of sound waves on the medium. Now that's different. Then it's going to introduce us to the elastic property of the medium and the inertial property of the medium. And sound waves are going to depend on if the medium is gas, liquid, solid, right? The other topic in this chapter that's left to cover is this topic of reflection and transmission of a wave. And it's such an important topic that it's also true for light waves or any other kind of wave. Whenever a wave comes and there's a certain interface and then the medium changes, certain important things happen at that interface. One of them is called reflection. The other one is called absorption or transmission, right? And that's such an important phenomenon because that's kind of how we see, this table is black. Why do I see this table as black? White light is coming and every color is being absorbed. Pretty much all the colors are being absorbed. Nothing is reflecting back. So black is the absence of all absorption, I believe. I mean, yes, so basically it's absorbing every color, and I'm seeing nothing, you know. In fact, if it was white, then it basically would be reflecting all the colors, and I would see a mixture of those colors as white. You see, if I see something red or orange, it's reflecting the orange. So certain important characteristics are happening, and with light waves, this is important. So they go through the whole. This is the formal mathematics of boundary conditions, right? What happens at the boundary between two mediums. So a wave is incident at the interface from the left, which upon encountering the interface produces a reflected wave in the left medium and a transmitted wave in the right medium. You see? So this equation here, incident wave, f of x t minus x over c sub l. Well, this is this equation right here. Right? That's the more general version of this equation. And it can apply to electric fields, sound waves, right? And then here what? This is the reflected wave. Why is it a plus here? Right? Because reflected wave, what's going to happen? This thing is going to switch on you and become positive. Right? So that means the reflected wave is going to the left. And then the transmitted wave is this. At the interface, we apply two continuity conditions. Continuity of velocity and continuity of stress. The velocity at the interface, in other words, you can't have a velocity be something here and then the velocity from the other side being something else. That's the idea of continuity from calculus, right? The velocity must be continuous function, you see. And then the other one is the stress on the thing, okay? So with the above two continuity conditions, we arrive at the solutions for the reflected and transmitted waves. H, phew, G, phew. Well, you can see kind of it's confusing. And then they go through and then they talk about it. But here, the good thing is they show you simulation. So what happened to the blue one? It seemed like most of the energy was transmitted. With the orange one, R is 2. What does the R factor mean? So depending on what the R factor is, how are they defining the R factor? So when you see some variable that you don't see, you always want to go back to see where did that R pop up first and what does its mean? How are they defining it? Where did it show up? R is Z sub R over Z sub L. The coefficients are shown below as a function of R. And then Z is equal to rho C is known as the mechanical impedance of a medium. So this is probably its density times the speed of light. Well, this one they're focusing on this light waves, right? So for us, how would we define our mechanical impedance? Instead of the density of the air, we would use the linear mass density of the string, right? So we could have, things are very similar. So we could have a similar equation and then define Z as what? Instead of density of the air, we'd say linear mass density of the string times the velocity of the wave in that string. And then the velocity of the wave would be square root of T over mu, right? So then R is equal to the Z of the reflected wave over the Z of the, what's this thing? I think that's the, is that an L? Looks like it's an L. wave over z of the L. So the coefficients are shown below as punctual. Some interesting points to note in the above plot. First, R is 0 corresponds to a free surface boundary. So what does that mean? First, if R is 0, I think this one is the z of the, it should say T, I don't know why they have L, because it's the z of the, I don't know why they're using L. Oh, okay, yeah, it came up over here. So you gotta kind of go back, speed of light. And then you got the speed of light.
Prepare for the tester. This is gonna save me.
Right. Oh, it's left, right. Oh, okay, okay, okay. So I'm kind of modeling for you how a lot of times reading these difficult books is a matter of being able to decipher, right? All the little subscripts they're using, all the little things. That's one of the hardest things. So you got to go back, okay, left, right. Okay, so their notation is left medium, right medium. So then you have here the wave incident is the speed of light in the left medium, speed of light in the left medium, so that's reflected wave. And then this is the speed of light in the right medium. Okay, I get it now. So now you get here z in the right medium over the z in the left medium. Okay, okay. So the z of the right, I was reading it as z reflected, and I see, what is this, you know? So it's not reflected, it's z right medium. So you got the left medium here. And then you will have here z of the left medium is going to be what? The density of the left medium. I'm applying it to our case now. The velocity of the left medium. And then z of the right medium is going to be the density of the right medium, velocity of the right medium. Right? Then their coefficient R is going to be the ratio of those, right? Okay, so then their coefficient R is going to be, it's here, z of the right over z of the left. So mu sub R, v sub R over mu sub L, v sub L. Okay, so let's write that here. And R is going to be Z sub R over Z sub L. So R is a unitless constant, therefore, right? So then if they're saying, if R is 0, what happens? If R is 0, that means the velocity in the reflected wave is 0. So that means there is no reflected wave, right? So that means all of the wave comes and transmits into the other medium. You see? So that would be something like a very transparent like the windows, you know. Most of the light that hits the window, let's say, transmits. Although there's very